Hello and welcome to this second lesson, section 2 of this chemistry course. Another moment, we're in section 2 looking at chemistry of the elements. Let's see precisely what we're doing in this video, shall we? Okay, we're looking at, first of all, group 7 elements, and in the second part we'll be starting to look at oxygen and oxides as well. Right, let's get straight in and look first of all at these group 7 elements. Now the group 7s are known as the halogens. Okay, known as the halogens, and start fluorine, chlorine, bromine, iodine, and acetylene. Now, because they're group 7, they've got 7 electrons in their outer shell. See, this example here is chlorine. Remember, it's got 17 there, tells us 17 electrons. That's 2, 8, and 7. It's 17. Now, to become stable, they need to gain an electron. So they gain the electron, they carry a charge of -1. Remember, electrons are negatively charged, so you gain an electron, you gain a charge of -1. So you end up with the ions Br-, I-, and also Cl-. Now all are non-metals. So here we've got 5 non-metals, low melting and boiling points, and that increases going down the group. So let's look at the states of these, shall we? Well, we've got fluorine is a gas, chlorine is a gas, bromine is a liquid, iodine is a solid, and so is acetylene. Okay? Now the halogens are diatomic. This means they always go around in pairs. So for example, chlorine gas is Cl2, bromine is Br2. Okay, so always go around in pairs, and they are brittle and crumbly when solid. These guys down here, these solids here, they're quite brittle and crumbly when they are solid. In general, with non-metals, they're poor conductors of heat and electricity, even when solid or liquid. Now, reactivity? Well, reactivity, going down the group, the halogens become less reactive. So fluorine is the most reactive, down at acetylene is the least reactive. Halogens react with other non-metallic elements such as hydrogen to form molecular compounds. So example here is hydrogen plus chlorine produces 2 molecules of hydrogen chloride. Now, hang about, you've seen this before, hydrogen chloride, HCl. Now, have you seen HCl before? It may be because you've seen it as hydrochloric acid. So the question here is, what's the difference between hydrogen chloride and hydrochloric acid? I mean, hang on a bit, they've both got the same formula, HCl. So what exactly is the difference? Well, this is the basic difference. Hydrogen chloride is a gas at room temperature, whereas hydrochloric acid is an aqueous solution, i.e. it's dissolved in water. And that is simply the difference between the two. Right, now, this is a bit of a tricky question, isn't it? This is off the specification. Explain in terms of dissociation why hydrogen chloride is acidic in water but not in methylbenzene. What a good question. Now you may be looking at this and thinking, what is this word here, dissociation? Well, what I'm doing is defining some of these key terms so we're really clear what they are. Let's define then dissociation. Now dissociation means, in simple terms, to separate or split into smaller particles or ions. Okay, so to separate or split into smaller particles or ions. So let's think now what we mean with hydrogen chloride. Now hydrogen chloride, as we said, is a covalent compound. We know that. However, when dissolved in water, what happens is it dissociates. That means it splits or separates the separate ions H+ and Cl-. The H+ ion gives it acidic properties. All the acids you know about, hydrochloric acid, sulfuric acid, nitric acid, they've all got the H+ ion, and it's that ion actually gives it its acidic properties. So, but when dissolved in an organic solvent, such as methylbenzene, hydrogen chloride does not dissociate into separate ions, so it does not show acidic properties. Okay, so you've got a difference there? Right, hope you haven't anyway. What it means is that when it's dissolved in water, it dissociates, leaving the ions H+ and Cl-. H+ gives it acidic properties. When dissolved in organic solvents, so methylbenzene, it does not dissociate. So dissociate here really is a key word, isn't it? Okay. Now let's think about the reactions to these halogens, shall we? Well, halogens react with metals to produce what we call ionic salts. Ionic salts, they must be therefore ionically bonded. The halogen atom gains 1 electron to form the halide ion, which, as we know, carries a charge of -1. For example, lithium, a metal, reacts with chlorine to form lithium chloride. Okay, so 2Li plus CO2 gives 2 LiCl. Now I think it would be really good to look at a video. So now we're going to YouTube and we'll look at a video prepared by the Open University that shows the 4 halogens and their reactivity.
Here are the 4 halogen elements: fluorine, chlorine, bromine and iodine. Fluorine on the left is almost colourless. Next comes chlorine, which is greenish yellow. Fluorine and chlorine are both gases at room temperature, but bromine is a liquid and iodine is a solid. Even so, they're both quite volatile. You can see the coloured vapours, orange-red above the liquid bromine and purple above the solid iodine. Whether solid, liquid or gas, the halogen elements consist of diatomic molecules F2, Cl2, Br2 and I2. Fluorine reacts often ferociously with almost everything else. A stream of fluorine instantly sets iron wool on fire, and it does the same thing to charcoal. Now let's see the reaction with hydrogen. There's hydrogen in the balloon. A jet of fluorine gas pierces the balloon and explodes with the hydrogen inside. Let's see it again in slow motion. Now you can see the fireball more clearly. Now the reaction between hydrogen and chlorine. I light the hydrogen at the jet and lower it into a jar of chlorine. The hydrogen carries on burning, but with a pale blue flame. When the halogens react with hydrogen, the hydrogen halides are produced: HF, HCl, HBr and HI. In each compound, the halogen has a valency of 1. All 4 compounds are gases. They're also very soluble in water. Here's water swallowing a jar of hydrogen chloride. Now let's see how the halogens react with aluminium. When aluminium powder meets fluorine gas, the reaction's over in a flash. To get chlorine to react with aluminium, I'll heat some foil in a stream of the gas. The white fumes are aluminium trichloride. With bromine, I just drop aluminium foil into the liquid. There's a short delay, but normal service is soon resumed. Once the reaction gets going, it quickly takes on the appearance of the pit of hell. As with the chlorine reaction, there's white smoke. That's aluminium tribromide. The reaction with iodine is just as spectacular. A little warming helps to get things moving, but once the reaction's off, it needs no further assistance. The products of all 4 of these reactions are white solids, and they're all trihalides: AlF3, AlCl3, AlBr3, and AlI3. Now aluminium is a trivalent element, so in these compounds the halogens are all showing a valency of 1. That valency of 1 is also satisfied when the halogen atoms bind to one another in the diatomic molecules with which I started this sequence.
Let's just summarise here reactions of halogens. So any halogen plus hydrogen gives what we call the hydrogen halides, and these are HF, HCl, HBr, HI. Now all 4 are gases and are very soluble in water. We've seen this with HCl, for example, for hydrochloric acid. Now halogens plus aluminium give what are called the aluminium trihalides, triminin 3. So AlF3, AlCl3, AlBr3, AlI3. And all 4 of these are white solids. Now, the specification also asks us to describe experiments to demonstrate that the more reactive halogen will displace a less reactive halogen from a solution of one of its salts. Whoa, let's just pause here a second and think about this term, displace. So, what does displace mean? Let's define it. In a displacement reaction, a more reactive element will displace a less reactive element from a compound. Okay, so in a displacement reaction, a more reactive element will displace a less reactive element from a compound. Let's look at a few examples, shall we, involving halogens. Now remember that the reactivity of halogens decreases as you go down the group. So fluorine at the top here is the most reactive, and acetylene down here the least reactive. Now think back to our work on alkali metals. Can you explain why there's this trend in terms of number of electron shells? Well, the key thing here, remember, is that the smaller the atom, the stronger the attraction of the outer electron. So fluorine here has got 2, 7. Okay, that means there's a very, very strong pull on the outer shell, and therefore it is very, very keen to gain an electron. Whereas down here, acetylene, it's a very, very big atom, therefore less strong. So that's why fluorine is more reactive than astatine. Okay, now we're getting what we call displacement reactions. Do you remember our definition? A more reactive halogen will displace a less reactive halogen from an aqueous solution of its salt. So potassium iodide plus chlorine, which of these two is more reactive? Well, remember last slide? Chlorine. So chlorine is going to kick iodine out of here and replace it. So this here we end up with 2 KCl, potassium chloride, plus iodine. If you look at the setup, if we've got here potassium iodide solution, if we bubble chlorine through it, the bottom of the solution starts turning like a purpley colour, which is in fact displaced iodine. Now what happens in the rest of the group? Well, this little table here will summarise it. Here we got the halogens. Okay. Now if we bubble chlorine through potassium bromide, because chlorine is more reactive, it will displace the bromine to end up with potassium chloride and bromine. Similarly here, because chlorine is more reactive, it displaces it, you get potassium chloride and iodine. Now bromine, because bromine is less reactive than chlorine, there will be no reaction with potassium chloride. But because bromine is more reactive than iodine, it will displace here from potassium iodide, displace the iodine to form potassium bromide, and iodine is therefore released. And poor iodine is so unreactive it can't displace potassium chloride and it can't displace either potassium bromide. Okay, so those are what we call displacement reactions. Wow, another difficult term here. Understand these displacement reactions as redox reactions. What is a redox reaction? Let's define it. A redox reaction is where both oxygen and reduction occur. Now you may come across oxidation as being the addition of oxygen and reduction as removal of oxygen, but hang about, we've got no oxygen here, so what else could it mean? Let's go back to the drawing board, shall we? What is this redox reaction? Well, if we lose electrons from an atom, it's known as oxidation. So if you lose electrons from an atom when you're forming an ion, it's known as oxidation. If it gains electrons, it's known as reduction. So if during a reaction atom gains electrons, therefore it's being reduced. Now this is known as oil rig. This way of remembering it. Oxidation is loss of electrons, OIL. Reduction is gain of electrons, RIG. Okay, that's where oil rig comes from. So just remember these 6 letters here, oil rig. Oxidation is loss, reduction is gain. Got it? I hope so. Now let's look at this in terms of halogen displacement reaction, shall we? Here we go. Potassium iodide, chlorine. Now potassium iodide is made of ions K+, 2I-. Why has this got a negative charge? Because it's gained an electron from potassium. It's gained a negative charge because it's gained an electron. Okay. Now chlorine will displace it. Chlorine now has a negative charge because it's taken on that electron, and iodine over there is by itself. Now what happens here? Iodine loses, because there's 2 in front, iodine loses the 2 electrons. Okay, to form iodine molecule over there, it's lost 2 electrons going from 2I- to I2. Now do you remember, oxidation is loss. Now iodine loses 2 electrons, oxidation is lost, therefore iodine has been oxidized. Okay, in this situation here, iodine has lost electrons, therefore it's been oxidized. Right, what's happened to chlorine? Well, chlorine, okay, the chlorine molecule, it has taken on the 2 electrons from potassium to become Cl minus. It has now gained electrons. Okay, that's what's got negative charges, gained electrons. Do you remember? Reduction is gain. So chlorine's gaining 2 electrons, therefore we must be able to say that chlorine has been reduced. Okay, chlorine has been reduced. Now, do you remember we were talking earlier about a redox reaction? Okay, with a redox reaction, there's a simultaneous oxidation and reduction. In this case, iodine has been oxidized by losing electrons, and chlorine has been reduced by gaining them. So that's what we mean by a redox reaction. Redox, R-E-D, stands for reduction, O-X, oxidation. Okay. Now, we've finished the group 7 elements. This is a big chunk here. It's a big chunk of stuff, oxygen, oxides. So what we're going to do is actually just try and cover the first bits here. Let's look first of all at what gases are in the atmosphere. Now I've got it in different forms here. Now nitrogen, of the air around us, 78% of the air around us is nitrogen. 21% is oxygen. Argon is just under 1%. And carbon dioxide, amazingly small amount, 0.04%. And over here, we've got it in pie chart form, 78%, 21%, argon 0.9, CO2, this is a bit accurate, 0.037, that's 0.04, isn't it? Now the atmosphere also contains tiny amounts of a few other gases, and also, depending on where you are, varying amounts also of water vapor. Now, we need to focus here on oxygen, and in particular, we need to explain how experiments involving reactions of elements such as copper, iron and phosphorus with air can be used to investigate the percentage by volume of oxygen in the air. Woo. What we're going to try and prove by experiment is this is actually 21%, and we'll look at 3 experiments we can do to actually prove that. But first of all, let's pick out 2. Let's pick out copper here and oxygen down here. Okay. Now let's look at the setup we might use to investigate this reaction. We can use a reaction between hot copper and oxygen to determine the percentage of oxygen in the atmosphere. So copper, 2Cu, plus oxygen, O2, gives copper oxide, 2CuO. Let's have a look now at the experimental kit. And here it is. What we've got copper turnings here, we've got 100 cc's of air at the start, and beneath it at a Bunsen burner. And this is taken from the BBC Bite-Size website. Now, let's look at this in detail, shall we? Okay, so here we are looking at this experiment here. Now, in here we've got 100 cc's of air, and the moment we're heating up this copper here, okay, the copper is being heated by the Bunsen burner, and it reacts with the oxygen inside the air. We keep moving the air back and forth. By using these syringes, we can move the air back and forth over the copper, so copper continues to react with the oxygen. Okay, we're forming copper oxide, and the oxygen's been taken out of the air. There we go, copper oxide's been formed. Now at the end of it, we've got 79 cubic centimetres of gas here. The volume at the start was 100, so we're left now with 21. Now that must have been how much oxygen there was present in the air originally. Okay, so work out percentage from the 21%. Follow that? So what happened was, we heated at the start 100 cc's of gas, we passed it over the copper reacted to form copper oxide. The volume at the end of the air in here was 79 cubic centimetres. Therefore the difference must have been the amount of oxygen that's combined with the copper, and it was 21 cubic centimetres. So we now know that 21 cubic centimetres of the air was in fact oxygen. And working out as a percentage, very nice easy figure there, it was 21%. So again, we've shown the volume, percentage volume of oxygen in the air is 21%. Now secondly, we can look at how iron and oxygen can react here. This is a bit more simple, this one here. All you've got here is a measuring cylinder here. You invert it into a beaker of water. Here's the water here. This is all that's in here is air, okay? And what you've done, you've stuffed up here a piece of iron wool. You then leave it for a couple of days. Now, guess what's going to happen? You've got water, you've got air, the iron wool is going to rust. Now rusting involves the formation of iron oxide, so oxygen is going to be absorbed from the air inside the cylinder. It'll keep doing this, it'll keep rusting and absorbing oxygen until there's no more oxygen left. So when there's no more change in the oxygen level, so the water level, sorry, the height of water inside the cylinder is measured, and from this we can work out the volume of air. Okay, quite a neat little simple experiment, isn't it? Okay, so you measure how much water's got in here. This, for example, is a 100 cc measuring cylinder. If this goes up 21 cc's, you know exactly how much you're in there. Clever, huh? Now, there's another way of doing it, looking at phosphorus and oxygen. Now, phosphorus and oxygen can be made to react together in a similar sort of way. Here we've got a setup over here. What we've got is a bell jar. The bell jar has been placed in a trough of water. You put coins down here at the bottom to make sure that water get underneath here and so can fill the bell jar if need be. Water is poured to the 0 level here. We then you float on a watch glass here a piece of phosphorus. Okay? And that floats on the surface. Now you put on that a hot metal rod. What that does, it ignites the phosphorus. So phosphorus starts to burn. Now, funny enough, as phosphorus starts to burn, it takes in oxygen. So as yellow phosphorus starts to burn, the airspace inside the jar fills with white fumes of phosphorus oxide. This dissolves in water to form an acidic solution. Okay, so it's burning, forming phosphorus oxide and using oxygen. So guess what? The level here is going to rise. As the phosphorus burns, it reacts with oxygen in the jar, so air in the bell jar, so water level rises as oxygen is used up. Again, you can work out how much this rises. It tells you the percentage of oxygen in the air. Another clever little experiment, isn't it? Now, good. Right, last little bit. How do we prepare oxygen in laboratory? Well, oxygen can be prepared in laboratory by what's called catalytic decomposition of hydrogen peroxide solution. For example, H2O2 goes to water plus oxygen. Now here, when we say catalytic decomposition, break this down using a catalyst, decomposition, breaking down, and the catalyst is MnO2. So manganese oxide is the catalyst used in this reaction. And we can see the apparatus here. What you'd have at the bottom here, you'd have manganese oxide, catalyst. You'd have up here hydrogen peroxide. You drip this onto the catalyst. As the hydrogen peroxide decomposes, oxygen bubbles off and is collected above water over here, and over here you're left with the water as a result of breaking up hydrogen peroxide. Right, pretty neat. Okay, we've done a lot in this lesson. Let's just check what we've done. We looked at group 7 elements, in particular chlorine, bromine, iodine. We looked at gases in the atmosphere and also looked at oxygen in the air as well. Okay, so thanks for listening and watching to this video, and I'll be back to you again very, very soon.